Okay, so I will then pass the mic to Ewan O'Connor for the Doppler wind lidars and radar wind profiler.
Okay, thanks, Nico. I hope you can hear me and you can see my mouse moving. Okay, so I'm going to introduce the remote sensing of wind to you. And so here I'm going to mainly be talking about Doppler lidars and the radar wind profiler, but also we'll mention SODARs as well. Okay, so if we think about these instruments, these are all active remote sensing in that they transmit a signal into the atmosphere and then look at the return. Okay, so there's, as I said, there's three main types. There's the wind profiler. Now what this does is it transmits in the microwave. You get scattering from turbulence in clear air. Whereas the Doppler LiDAR, you're transmitting light. And the main scatter you're thinking about here is aerosol. And then for SODAR, you're transmitting sound and you're actually getting scattering back from atmospheric turbulence. Okay, so all of these, what they're really doing is measuring the radial Doppler velocity. And the important thing to remember is you're actually looking at the component along the line of sight, and I'll explain that in a little minute. Okay, so the maturity of both the radar wind profilers and the SODAR, they are mature, they've been around for some time. The Doppler LiDAR, at least in a commercial sense, is relatively new, but is also maturing. Now, in some ways, these networks are relatively sparse, but they are increasing over time. Okay, so the main thing we're doing with any of these instruments is measuring the radial Doppler velocity. Okay, so what does that look like? The idea here is, if you imagine, I'm looking at the bottom part here, this would be a 2D plot of if you were scanning horizontally, what you would do is you'd measure the wind speed, and here it's going from blue is negative wind speed to red is a positive wind speed. Okay, and then you would actually be able to identify the wind direction from this. But however, what we really want is the vertical profile. Okay, so now what we do is we have to scan. And then what you're actually looking at here is if we do a scan of some sort, we're actually trying to now identify the component of the wind that we measure. Because remember, we are actually measuring along the line of sight, but we want the horizontal component. So that's the main question, is how do we retrieve this horizontal component, which is the wind? Okay, so there's a number of ways of doing it. The common ones are Doppler beam swinging, which is called DBS, and then I'll introduce the VAD, which is the conical scan. So here the idea is you have three beams. One is pointing vertically, and then two of these beams are off zenith. So they're normally, say, 20 degrees away from vertical. And the idea then is between these two, if they're orthogonal to each other, you can actually measure the components in the two directions. Okay, and then with using trigonometry, you can then actually derive the horizontal component, which is what you want, and then you would get the horizontal wind speed. And the point is, because you're normally sending out in pulses, you actually get this, rather than this just being, you actually get range gates here, so you actually get a vertically resolved component, and that's how you actually get your profile. A little bit more advanced, if you can do it, you can actually do scanning at a constant angle, and you change the azimuth. So you send up a load of scans like this, and then again you're getting the horizontal component, and then you can use trigonometry to then try and estimate your horizontal wind. Okay, so if we think about the sort of instruments that are available at the moment, a common one. The common wavelengths these days for Doppler LiDARs, especially for the commercial systems, is 1.5 to 2 microns. So there's very specific wavelengths that they use, and this is because they're using telecommunications technology, and this actually means that the systems are relatively cheap to what they used to be. Now, just to let you know, that some of these instruments do actually come with a depolarization channel, but most don't. Another thing that's certainly is the case at the moment, that the technology is advancing very quickly. So there's lots of updates, especially in the last 5 years or so. Okay, so if we think about the sort of things that you might have heard of, there's two main companies that are providing quite small instruments. By this, I mean less than, say, 100 kilos. In other words, 2 people can carry them. So these are truly mobile. This would be the Leosphere systems, which are now owned by Vaisala. So this would be the WinCube 100S, 200S, 400S. And here I'm referring to instruments that can scan all the way to the top of the boundary layer. And then Halo Photonics also do this where they have a streamline range. There's a streamline, the Pro and the XR, which are also similar to this in that they have slightly different capabilities. And again, all of these, nearly all of these, are full hemispheric scanning. So they can scan anywhere in the hemisphere. So you can choose your own scan pattern. Other instruments that are much larger, Mitsubishi, Leonardo, and Lockheed Martin do also make Doppler lidars, but these are much, much larger. So these are container-based. These are a few tons, and there are a few of these at airports. But these are normally used more for measuring things like shear near airports. Okay, but these systems are still used in the research arena. But bear in mind, if you look at the size of these, okay, they might be more sensitive, but they're also quite a lot more expensive. When we think about radar wind profilers, again, there's a few frequencies that they can operate at. And if we think about ones that can actually see the whole of the boundary layer, there tends to be two sets at the moment. So one is these sort of longer frequencies, so 400 to 500 megahertz, normally called UHF. Here's an example here from Bayreuth in Germany. Now these are quite large, so that would be about 50 meters square, this sort of instrument here. And then there's this other range which are operating at slightly higher frequencies, and they're much smaller. So this is now more, say, 5 meters by 5 meters. Okay, so the first one, this one here can see all the way to the tropopause and probably much further, whereas this one can usually see to about 1.5 to 2 kilometers. So we'll cover the boundary layer. And if we go for SODAR models, again, I'm only thinking about the extended altitude range instruments, so ones that can see above 1 kilometer. Again, there's two main manufacturers here, which are Remtech and Metech. And again, this is probably about, say, 5 meters by 5 meters. So these are much larger than some of the instruments that are quite often used for nearer surface profiling. Okay, so what are the challenges for most of these? Generally, these instruments operate 24/7, continuously, and there's not really any issues with regards to keeping them operating. It's just the actual data availability might be hampered by strong winds. So if you have very, very strong winds, then you might exceed the measurement range of the instrument. And if it's very strong winds also for the SODAR, then it actually means that there's too much noise. For radar wind profilers, you have to think about birds and wind farms. You actually see these in the data, so you'd have to be able to deal with that. And then for Doppler LiDAR and radar wind profilers, especially at higher frequencies, precipitation is also an issue. I think that precipitation is generally an issue for most LiDAR types anyway. Since all of these instruments actually depend on there being enough signal, for Doppler LiDARs, if you have a very, very clean atmosphere, then again, your signals aren't so good and you can't always see as far as you would like to. And also clouds and fog are also a bit of a problem. But generally, for the instruments I've shown here, they can all see to the top of the boundary layer during most conditions. And actually, rather than it being a signal to noise issue, so there's always enough signal to get a retrieval, actually, when it comes to retrieving the winds, the issue is to do with the homogeneity. So when you're doing your scan, you're assuming that everything is homogeneous, and that's not quite true, especially when it's strongly turbulent. We can identify this, and we can actually mitigate this a little bit by how we're doing the scanning. So that's a lot of the work that we're doing at the moment during this probe project. So careful processing is also key for these instruments. For example, if we think about what's been done in previous actions or the current action, things like radar wind profiler there's been a lot of work on bird clutter processing, and we've been actually looking at how you actually derive the velocity uncertainty for the instruments. Do you have to perform background corrections? And one of the interesting ones is how you're doing the scan selection optimization for wind profiling. So if you're interested in capturing the whole of the boundary layer, how best to do that? And there's a few other things that we're also looking at. And one of the important ones is the impact of turbulence on the wind retrieval. In other words, when is your assumption valid? If we think about advanced products, if we think about, we can obviously, once you have your wind profile, you can get wind shear and then immediately provide wind shear alerts. And if we're looking at the high temporal variation in velocity, we can use this actually to give us the turbulent properties. So that although there might be a problem for deriving winds, we can actually still use those to actually find out more about what the turbulent properties are. And we're thinking about the different instrument advantage. The SODARs have a strong advantage in very shallow boundary layers, as in those less than 100 meters deep, because these are the other instruments that tend to be limited to 100 meters or even 500 meters in the case of the radar wind profiler. The advantage of the radar wind profilers is that they can get the boundary layer top all the way to the boundary layer top. So not just to the base of the cloud, but they can go above that. And again, sometimes the disadvantages can also be turned into advantages. So there's actually plenty of cases now where the radar wind profilers are actually looking at bird migration monitoring. So you can actually follow when the birds are ready to migrate. And another thing that, if you can do all the corrections correct, you can actually also use a Doppler LiDAR in the same way as an ALC, which will be talked about later. Again, other interesting things we can do is detection of low-level jets. So here we have a profile of time, height, profile of wind speed. And you can see that we have strong winds here in the orange and green of over 10 meters per second, while it's calm, say 5 meters per second above and below. You can see here in the wind direction, there's wind shear associated with that. And we also even have the turbulence associated with that. Okay, and that means that we can actually start to run through this and actually get low-level jet climatologies, which has been part of the work of the previous action. And the other thing that we're also doing, especially now that we have winds and turbulence, we can start to do things like combining multiple Doppler LiDAR products to then get towards things like boundary layer classification. So the idea is we can actually have our plots of wind shear, skewness, and dissipation rate, combine these and get a classification, and then we can actually take that further to say something about where is the mixing? Is this mixing connected to the surface if you're interested in dispersion? And also what is the source of the turbulence? Because it could be the clouds, it could be the surface, or it could be shear. Okay, so there's a lot of work going on in this field, and join the action to find out more.